Things do get more and more interesting as we go along. The possibilities we can imagine keep on increasing. I am so tempted to say something about the fun really beginning, but I am pretty sure that it is a phrase that students do not like to hear from teachers. We have been doing a lot with capacitors and inductors. Now we're going to go back and combine capacitors with operational amplifiers. Here we will start to glimpse the gem-like quality of circuit analysis. What I mean by that is when one holds a gem in the light, every time the gem moves, the gem appears different. Nothing about the gem has changed, only the light passing through the gem and our perspective has changed. When we analyze a circuit, so much of what we see is going to depend on the perspective from which we approach the analysis. We have already seen that components can look very different to different types of sources. A capacitor, for example, can look like an open circuit to a DC voltage source, whereas if we apply a low-frequency sinusoidal source to the capacitor, it may look like a relatively large impedance. A very high-frequency sinusoidal source may make the capacitor appear like a short circuit. These are all examples of the source changing, resulting in the component appearing different. Sometimes we can analyze the same circuit with the same components under the same circumstances and still see something different. We are familiar with at least two completely different ways of looking at circuits. We have been taking circuits from what we call the time domain to the phasor domain for analysis, and then taking the solution back to the time domain for interpretation. First, I would like to say that we can do analysis in the time domain. Secondly, I should point out that there are more domains. Many more domains. I said we were going to look at operational amplifier circuits with energy storage devices. Today, by energy storage devices, I mean capacitors. Using capacitors will illustrate the points I intend to just fine, and they are more commonly used in conjunction with operational amplifiers. Looking at a very basic inverting configuration of an operational amplifier, I could substitute a capacitor for the input resistor. To make things simple, this will be an ideal operational amplifier. Let us make sure we remember the properties of an ideal operational amplifier. An ideal operational amplifier has an infinite input resistance. That means no current enters the two input terminals. An ideal operational amplifier has an infinite gain. That means there will be no voltage difference between the two input terminals. The ideal operational amplifier has no output resistance, therefore the current that leaves the output terminal can be anything. Now we can begin our analysis. Since the non-inverting terminal of the operational amplifier is grounded and there is no voltage difference between the two input terminals of the operational amplifier, the inverting input of the operational amplifier is also at 0 volts. We can then indicate directions for the current through the capacitor and the resistor. We can write a KCL equation at the inverting terminal of the operational amplifier. The current through a capacitor is equal to the capacitance times the derivative of the voltage across the capacitor. In this case, the voltage across the capacitor is the input voltage minus the 0 volts of the inverting terminal of the operational amplifier. So the current entering the node is the capacitance times the derivative of the voltage. The current leaving the node through the resistor can be written as 0 volts minus the output voltage divided by the resistor. Multiplying through by the resistance and eliminating the zeros gives us this. Looking at our output voltage, we see that it is a constant times the derivative of the input voltage. Since the output of the circuit is a constant times the derivative of the input, we call this a differentiator. What if we switch the position of the capacitor and the resistor? We will begin our analysis in the same way. Assuming an ideal operational amplifier, the first step is applying the ideal assumptions. An ideal operational amplifier has an infinite input resistance, therefore no current enters the input terminals. An ideal operational amplifier has an infinite gain, therefore there is no voltage difference between the input terminals. The op-amp also has no output resistance, therefore the output current can be anything. Since the non-inverting terminal of the operational amplifier is grounded and there is no voltage difference between the input terminals of the operational amplifier, the inverting terminal is at 0 volts. We can write a KCL equation at the inverting terminal. Putting arrows in for the directions of our currents, the current through the input resistor is the input voltage minus 0 volts divided by the resistor. The current that leaves the node will be the capacitance times the derivative of 0 minus the output voltage. These are the only two currents at the node, so we can proceed by arranging the terms so that we have the derivative of the output voltage with respect to time is equal to minus 1 over R1 C2 times the input voltage. We can integrate both sides of the equation and determine that our output voltage is proportional to the integral of the input voltage. For now, I am ignoring any constant term that results from the integration. We'll just say the initial voltage across the capacitor was 0 volts. This circuit is then an integrator. so we can take derivatives and do integrals of signals. These two circuits were quite easy to analyze. However, they do suffer from a significant flaw, especially the integrator. The problem is that the capacitor blocks DC. If there is any DC present, the capacitor will look like an open circuit. Remember that the feedback from the output to the inverting terminal is what makes the amplifier stable. An open circuit in the feedback means that the open loop gain will apply to any slight offset voltages that might exist at the input. A millivolt can easily be enough to cause the operational amplifier to saturate. In addition, for any periodic function, the gain of the amplifier will depend on the frequency of the input to the point that the gain increases or decreases without a mathematical limit. This can be corrected by a rather simple alteration of the circuit. For the integrator, adding a resistor in parallel with the capacitor will correct for the open loop gain problem and make the circuit stable. To analyze a circuit, beginning with applying the ideal assumptions about the amplifier, no current enters the inputs of the amplifier, there's no voltage difference between the inputs of the amplifier, and the output current of the amplifier can be anything, and since the non-inverting terminal of the operational amplifier is grounded, the inverting terminal will also be at 0 volts. Indicating directions for each of the currents at the inverting terminal, we have the current through R1 has to be equal to the current through the capacitor plus the current through the resistor R2. Looking at the equation, we can rearrange it to see that it contains the input voltage and the output voltage and the derivative of the output voltage. We are probably not quite ready to solve this. However, if we look at the circuit a little bit differently, we can analyze it without having to deal with a differential equation. I converted the capacitor to something that looks pretty close to an impedance. Instead of j omega, however, I used S. For now, we can pretty much treat them as the same thing, but you will notice that the background is a slightly different color to indicate that this is not the time domain, nor is it the phasor domain. Indicating the ideal assumptions on the circuit diagram, noting that the non-inverting terminal is grounded, and applying that voltage at the inverting terminal, I will then indicate the direction for the three currents at the inverting terminal. The current that enters the node is the input voltage minus 0 volts divided by R1. The current through the capacitor leaves a node and is written as 0 minus V out over 1 over S C2. Again, if it helps for now, treat S as j omega. The current through R2 also leaves the node and is written as 0 minus V out over R2. Eliminating the zeros from the equation gives us the following, and we can factor out the negative sign and V out from the equation. Instead of solving for V out in terms of Vn, I am going to solve for the ratio of the output voltage to the input voltage. This is called the transfer function of the circuit. Factoring 1 over R2 out of the denominator results in the output voltage over the input voltage being equal to minus the ratio of the two resistors times 1 over 1 plus S times R2 C2. Well, that is interesting. So what does it mean? Remember that for this problem, we can treat S the same as j omega. To make it a little easier to think about, we can put some numbers in. Let us make R1 equal to 20 kiloohms, R2 equal to 200 kiloohms, and the capacitor equal to 3300 picofarads. That results in the product of R2 and C2 having units of microseconds. Yes, the product of ohms and farads is seconds. Check it yourself. You should always check everything yourself. So, if S corresponds to j omega, R2 times C2 would relate to an angular frequency of 1.52 kiloradians per second. Why would that matter? Well, if S is j omega, then when the angular frequency is about 1.52 kiloradians per second, the denominator becomes 1 plus j. Converting to polar form, the denominator becomes the square root of 2 times e to the j 45 degrees. Focusing on just the magnitude for now, that means that the magnitude of the output with respect to the input has been reduced by a factor of 1 over the square root of 2. That is a special number. Remember that power is proportional to the square of voltage. So when the magnitude of the voltage is divided by the square root of 2, the output power has been reduced by a factor of 1/2. One of the names for the angular frequency where this occurs is the half power frequency. Other names include the cutoff frequency, the 3 dB frequency, the corner frequency, the break frequency, to name a few. Back to interpreting the transfer function. If S, or the angular frequency, is very small, the transfer function basically becomes the output of an inverting operational amplifier. If S becomes very large, say at high frequency, then the transfer function goes to 0. That means that this circuit attenuates high-frequency signals. We call this an active low-pass filter. It is active because it has a gain for a certain range of frequencies, in this case 10 volts per volt. It is a low-pass filter because only signals with frequencies below a certain point get through the amplifier. Using these numbers, if we plot the magnitude of the output as a function of the angular frequency, we get this graph. Note that when the magnitude is reduced by a factor of 1 over the square root of 2, we are at the frequency determined by 1 over the product of R2 and C2. The circuit we just analyzed, by the way, is called a Miller integrator, named for the pioneering electrical engineer John Milton Miller. Unlike the basic integrator that I first showed, the Miller integrator does not integrate a sinusoid until the frequency is an order of magnitude higher than the half-power frequency, and really it should be 2 orders of magnitude. If we move the capacitor from the feedback to the input branch, we might expect to get some sort of differentiator. There's only one way for us to find out. Besides looking it up, what fun is that? Here is such a circuit to analyze. The resistor values are the same, but I increased the size of the capacitor to 330,000 picofarads. For now, we will analyze the general case without any values. We can put the numbers back in at the end if we want. The analysis of any ideal operational amplifier begins with applying the ideal assumptions to the amplifier. I have been asked why I insist on writing these assumptions every time. There are several reasons. A simple one is that if we do everything the same way every time, we will get the same results. More importantly, any good analysis opens up with the assumptions that are being made. If we make assumptions without asserting the assumptions, eventually we forget that they are assumptions at all. That leaves us very vulnerable to not being able to deal with real circuits. It is also very important to not just know what the assumptions are, but where they come from. That allows us to quickly identify when a non-ideality manifests. With all that being said, an ideal operational amplifier has an infinite gain, therefore there is no voltage difference between its input terminals. An ideal operational amplifier has an infinite input resistance, therefore no current enters the input terminals. An ideal operational amplifier also has no output resistance, therefore the current at the output terminal can be anything that it needs to be. The voltage at the non-inverting terminal is 0 because it is grounded. That means the voltage at the inverting terminal will also be 0 volts. Indicating directions for the current entering and leaving the node connected to the inverting terminal, we can write an equation for the current through the input branch that is equal to the input voltage minus 0 volts divided by the sum of the input impedances. That has to be equal to the current through the feedback resistor, which is 0 minus Vout divided by R2. If we simplify the appearance of the equation by eliminating the zeros, we can solve for the ratio of the output voltage to the input voltage and determine that the transfer function is equal to the negative of the ratio of the feedback resistor to the input resistor, times 1 over the quantity of 1 plus 1 over SR1C1. This is not a proper form for a fraction. The proper form would look more like this. However, I believe the improper form is easier to interpret. So looking at the improper form and remembering the component values that were shown on the schematic, the product of R1 times C1 will be 6.6 milliseconds. That would correspond to an angular frequency of 152 radians per second. In this case, large values of S result in the denominator approaching 1. That means the transfer function is simply the negative of the ratio of the resistances. For small values of S, or at low frequencies, the denominator becomes very large, making the output approach 0. Therefore, this is an active high-pass filter. It is active because it has a gain. It is high-pass because low frequencies are attenuated. A plot of the output magnitude versus the angular frequency would look like this. Note again, when the magnitude is reduced by a factor of 1 over the square root of 2, it corresponds to the frequency indicated by 1 over the product of the resistance times the capacitance. These are two of the most basic active filters. We can adjust the frequency that either of these filters passes or removes by changing the values of the resistances and capacitances. It may also be pretty obvious that we could use these filters back to back to allow only a certain range of frequencies to pass. It is also possible to create filters that remove the undesired frequencies more aggressively. I think, however, that with these two filters we have enough to discuss for a little while. Today we looked at operational amplifier circuits that included capacitors. We found when we analyzed the circuits in the time domain that we were able to take derivatives and do integrals of the input signal. We looked at the major flaw of the basic integrator and differentiator. We then found a simple solution to overcome that flaw. This, however, increases the difficulty of our analysis, so we were introduced to the letter S, which will eventually be named. For now, it was a substitute for j omega. We then developed the transfer functions for the active high-pass and active low-pass filters. There's much more to unpack, but for now, go out and make it a great one.